There's a moment that happens when you truly understand the size of the universe, and it doesn't feel like understanding at all. It feels like vertigo. I was 8 years old, lying on my back in an empty field, looking up at the night sky. My uncle had just pointed out that the light from some of those stars had been traveling through space for longer than humans have existed. He said it casually, like he was describing the weather. But something about the way he said it, the finality of it, the matter of factness, short circuited something in my brain. Not because it was the first time I'd heard the idea. I'd heard it before, but I'd never felt it. The feeling was this: those points of light are not in the sky. The sky is not a dome with lights attached to it. Those lights are impossibly far away. And if they're that far away and they're this bright, then they must be enormous. And if they're enormous and there are so many of them and they just go on forever, I remember thinking I was going to fall off the earth, not upward toward the stars, just fall away entirely into the enormity of it. The feeling passed. I sat up. I felt sick in a way I didn't have words for. That night changed how I thought about existence. Not immediately. I was 8. And there were other things to think about, like video games and lunch. But it planted something. A question I didn't know how to ask. What does it mean that the universe is that big? I've spent a lot of time thinking about that question since then. Reading cosmology, learning the actual numbers, trying to build conceptual frameworks for understanding scales that the human mind isn't really equipped to grasp. Because here's the problem: we evolved to perceive scale at human dimensions. A few meters, maybe a few kilometers if you're thinking about the horizon. Our brains are good at understanding whether something is a tenth of a kilometer away or 10 kilometers away. The difference is obvious to our intuition. But what about a million kilometers or a billion? Our brains start failing at these scales. They don't fail catastrophically. We can do the math, we can understand the ratios, but we can't feel the difference the way we feel the difference between a meter and a kilometer. This is a challenge I've thought about deeply. How do you convey the size of the universe to people? How do you make something comprehensible when it's fundamentally too large for human intuition? I don't think the answer is just numbers. Numbers alone don't create understanding. A million kilometers and a billion kilometers are both numbers, but they don't feel different. You can see the ratio, 1,000 to 1, but that doesn't create understanding. It creates a kind of intellectual acknowledgement that one is bigger than the other. That's not the same as understanding. The answer is probably a combination. Numbers, yes, but also analogies, comparisons to things you can understand, personal perspective, thought experiments that let you think your way into comprehensions, even if you can't feel your way there. So that's what I want to do in this video. I want to help you understand how big the universe actually is. Not just know it intellectually, but grasp it, really grasp it as much as possible. Let's start small. Let's start with something you can actually perceive, something in your immediate experience, and then we'll build outward. The moon is the closest celestial body to Earth. It's been with us for billions of years. It controls our tides. It lights our night sky. It feels close. When you look up at the moon, it feels like it's in the sky with you, relatively speaking. On clear nights, I can see the moon's craters without any equipment. It feels intimate. It feels near. The moon is 384,000 kilometers away. That's the first number. Let me give you a sense of what that means. If you drove a car at 100 kilometers per hour, sustained, no stops, driving continuously. It would take you 384,000 hours to reach the moon. That's about 44 years. 44 years. Driving nonstop the entire time. That's longer than many people live. That's longer than a typical career. That's a significant portion of a human lifespan, spent in a car, traveling towards something that appears so close in the night sky that you feel like you could reach out and touch it. The moon is close enough that it's technically in our neighborhood. Cosmically speaking, it's practically touching us. And yet, if you tried to reach it using human transportation, it would consume most of your life. Let me give you another perspective on this. The fastest spacecraft we've ever built, the Parker Solar Probe, travels at about 165 kilometers per second. Even at that speed, it would take roughly 32 hours to reach the moon. That's longer than a typical cross-country flight. And our fastest spacecraft is moving at speeds that would liquefy you if you tried to go that fast in a car. The moon is 384,000 kilometers away. Light from the moon takes 1.3 seconds to reach Earth. When you look at the moon, you're seeing it as it was 1.3 seconds ago. That's not very long, but it's still the past. Now, the sun is farther, much farther. The sun is 150 million kilometers away. Again, let's put this in perspective. That 100 kilometers per hour drive, now it's 150 million hours. That's about 17,000 years. 17,000 years. That's more than twice as long as recorded human history. That's longer than the entire span of human civilization. If you left today in a car driving at highway speed without stopping, without sleep, without maintenance, assuming your car never broke down and you never got tired, you wouldn't arrive for 17,000 years. Your great, 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 great grandchildren across many generations might finally arrive. And here's the thing, the sun doesn't feel that far away. When you look at the sun safely through special glasses, it looks close. It feels like it's in the sky with you, relatively nearby. It's your personal star. It warms you. It gives you light. You feel its heat on your skin. The relationship feels intimate and immediate. But if you drove toward it without stopping, it would take 17,000 years to get there. Light from the sun takes 8 minutes to reach Earth. When you look at the sun, you're seeing it as it was 8 minutes ago. Every photograph of the sun you see is at least 8 minutes old. This is starting to illustrate something important. Our intuitive sense of distance is completely wrong at cosmic scales. The moon looks close and is 44 years away by car. The sun looks close and is 17,000 years away by car. Objects that appear to be in the sky with you are actually impossibly far away. Now let's expand the scale a bit more. The sun is the center of our solar system. Planets orbit around it, but the solar system is large. Mercury orbits closest to the sun, about 58 million kilometers away. Venus is 108 million kilometers. Earth is 150 million. Mars is 228 million. And then the gas giants are much farther out. Jupiter is 778 million kilometers from the sun. Saturn is 1.4 billion kilometers. Uranus is 2.9 billion kilometers. Neptune, the farthest major planet, is 4.5 billion kilometers away. Let's pause on Neptune for a moment. Neptune is 4.5 billion kilometers away. That's 45 million kilometers away by the 100 kilometer per hour car metric. That's 45 million hours of driving. That's about 5,000 years. Neptune is one of the planets in our solar system. It's still part of our immediate cosmic neighborhood, as much as we can call anything immediate and close in cosmic terms. And yet, it would take 5,000 years to drive there. But here's the thing, even Neptune isn't the edge of the solar system. Beyond Neptune is the Kuiper Belt, a region of icy bodies including dwarf planets like Pluto. The Kuiper Belt extends from about 30 astronomical units to 55 astronomical units from the Sun. Beyond that is the Oort cloud, a hypothetical shell of icy bodies that marks the true extent of the Sun's gravitational dominion. The Oort cloud is enormous. It extends out to roughly 100,000 astronomical units from the Sun. An astronomical unit, an astronomical unit is the distance from the Earth to the Sun, which we just established is 150 million kilometers. So the Oort cloud extends to 100,000 times the Earth-Sun distance. That's 15 billion kilometers, that's 150 million years by the 100 kilometer per hour car metric. 150 million years. That's longer than modern humans have existed as a species. That's longer than any individual species has existed on Earth in its current form. That's a timescale that dwarfs human history, geology, and biology. The solar system, from the Sun to the edge of the Oort cloud, is incomprehensibly large. And yet, it's just the beginning of cosmic scale. Everything I've described so far, the Moon, the Sun, all 8 planets, the Oort cloud, all of this is what we might consider our immediate neighborhood. This is what belongs to our solar system, and it would take 150 million years to drive across it. Let me introduce a unit that makes thinking about cosmic scale easier. The light year. A light year is the distance that light travels in 1 year. Light is the fastest thing we know of. It travels at 300,000 kilometers per second. In a year, 365 days, light travels about 9.4 trillion kilometers. 1 light year equals 9.4 trillion kilometers. To put this in context, the Sun-Earth distance, which we call 1 astronomical unit, is about 8 light minutes. Light takes 8 minutes to travel from the Sun to Earth. Neptune is about 4 light hours away. The outer edge of the Oort cloud is about 1 light year away. That's significant. The entire solar system, the collection of objects that orbit the Sun, is only about 2 light years across. Light takes 2 years to traverse it. A car at 100 kilometers per hour would take 300 million years. Now we can expand further into the universe. The nearest star to the Sun, other than the Sun itself, is Proxima Centauri. It's 4.24 light years away. This means that the light we see from Proxima Centauri today left that star 4.24 years ago. When we look at Proxima Centauri, we're seeing it as it was in 2020, if we're observing in 2024. We're seeing the past. Proxima Centauri is the closest star. It's our nearest stellar neighbor, and it's 4.24 light years away. That's 40 trillion kilometers. That's 400 million years by car. To put this in perspective, if you started driving to Proxima Centauri when the earliest human civilizations were emerging 10,000 years ago, you still wouldn't be close to arriving today. You'd have barely begun your journey. You'd still have more time remaining than all of recorded human history. The next nearest star system is Alpha Centauri A and B at 4.37 light years. Then Sirius at 8.6 light years. Then gradually more distant stars as you scan the night sky. Stars like Vega at 25 light years, Altair at 17 light years, Polaris at 430 light years. I want you to notice something. We've moved from the moon, 44 years by car, to Neptune, 45 million years by car, to Proxima Centauri, 400 million years by car, to distant stars, billions of years by car. We're seeing the exponential growth. Each step outward is vastly, incomparably larger than the previous step. The scales aren't just bigger, they're incommensurable. The ratio between one scale and the next is often a million or a billion. Now let's think about the Milky Way galaxy. Oh, the Milky Way is a spiral galaxy. It's disc-shaped, rotating, with a bulge at the center and graceful spiral arms extending outward. The galaxy is about 100,000 light years across. The solar system is about 2 light years across. The Oort cloud is about 2 light years across. 100,000 light years. Let me try to convey what that means in comparative terms. Light from one edge of the Milky Way to the other takes 100,000 years to cross. The oldest human civilizations we know about are roughly 10,000 years old. So light from one side of our galaxy has been traveling for 10 times as long as human civilization has existed, and it's only part way across the galaxy. To put this another way, if you were born when the oldest pyramids were built in ancient Egypt, and you lived for 10,000 years, far beyond any human lifespan, light from one edge of the galaxy would still be traveling toward the other edge. Your entire extraordinary lifespan would represent just 1/10 of the time it takes light to cross the galaxy. The Milky Way contains an estimated 200 to 400 billion stars. Let's use 200 billion as a conservative estimate. That's 2 times 10 to the 11th power stars. 200 billion is a hard number to grasp. Let me try a comparison. The world population is about 8 billion people. So the Milky Way contains about 25 times more stars than there are humans on Earth. Every person on Earth, if they each represented 25 stars, would together represent the entire stellar population of the Milky Way. Or here's another way to think about it. If every person on Earth had a telescope and looked at the sky, and each person could somehow observe a different star, you'd still have 192 billion stars left over that nobody was looking at. If you divided all the stars in the Milky Way equally among every person on Earth, each person would get about 25 stars. That's your personal allocation of stars. 200 billion stars. Just in our galaxy. Just in one galaxy out of billions of galaxies. And the Milky Way is a galaxy, but it's not the whole universe. Not even close. In fact, the Milky Way is not even the largest galaxy we know of. The universe contains galaxies much larger than ours. IC 1101, for example, is an elliptical galaxy that might contain up to 100 trillion stars, 1,000 times more than the Milky Way. It's 4 million light years across. It's almost incomprehensibly massive. But IC 1101 is a monster, an outlier, an extreme case. Most galaxies are much smaller than the Milky Way. The average galaxy contains only about 100 million stars, 1,000 times fewer than the Milky Way. Our galaxy is actually quite large by typical standards. But the Milky Way itself is large enough that we're starting to strain the capacity to comprehend. Now, beyond the Milky Way are other galaxies. Lots of them, billions of them as far as we can see. The Andromeda Galaxy is our nearest major galactic neighbor at 2.5 million light years away. Andromeda is a spiral galaxy like the Milky Way, possibly somewhat larger. It contains roughly 1 trillion stars, 5 times as many as the Milky Way. It's an island universe comparable to ours in size and complexity, yet separated from us by 2.5 million light years of mostly empty space. Beyond Andromeda are billions of other galaxies. The deeper we look into the universe, the more galaxies we see. The deepest images from the Hubble Space Telescope show galaxies as far as we can see, out to 13 billion light years distant. At these distances, we're looking not just far away, but far back in time. Light from a galaxy 13 billion light years away left that galaxy 13 billion years ago. The universe is only about 13.8 billion years old. So we're seeing galaxies as they were when the universe was very young, just a few 100 million years old. Let me pause here and let this sink in for a moment. We live in a galaxy that's 100,000 light years across and contains 200 billion stars. That galaxy is one of billions of galaxies scattered throughout the universe. Some of those galaxies are close. Andromeda is a mere 2.5 million light years away, which sounds far until you realize it's actually our nearest neighbor. Most galaxies are vastly farther. There are galaxies so far away that their light has been traveling toward us for nearly the entire age of the universe. And all of this is what we can see. The observable universe, the part of the universe we can in principle see from Earth, extends out to about 46 billion light years in every direction. The reason it's 46 billion light years rather than 13.8 billion light years is due to the expansion of space itself. Space has been expanding since the Big Bang, stretching, growing. So even though those distant galaxies are 13.8 billion light years away in terms of how long ago the light left them, the space between us has expanded. The co-moving distance, the actual current distance accounting for expansion, is about 46 billion light years. 46 billion light years. That's the horizon of the observable universe. That's as far as we can see, given the age of the universe and the speed of light. But here's a crucial point. The observable universe is not the whole universe. It's just the part we can see. The actual universe might be much, much larger. It might even be infinite. We don't know. If the universe is truly infinite, then beyond the cosmic horizon, beyond those 46 billion light years, there's more of everything. More galaxies, more stars, more planets, more structures continuing on forever. Not just far away, but infinitely far away. Not just many, but infinitely many. The concept of an infinite universe is deeply challenging. Our brains evolved to deal with finite spaces, finite quantities, finite possibilities. Infinity is not a number. It's a concept that resists intuition. An infinite universe means there's no edge, no boundary, no place where things stop. Just more and more and more, forever. When I was 8 years old, lying in that field, my uncle told me about light years. But I don't think he conveyed the full scope of what that means. I don't think I could have grasped it. I'm not sure anyone can truly grasp it. It's beyond the scale that human intuition can handle, but we can reach toward understanding through analogy and reason. Let me try to build some intuition by thinking about size in different ways. One way to think about scale is density. How crowded is space? How much stuff is out there? Here's an interesting fact. Space is almost entirely empty. If you took all the matter in the observable universe and spread it evenly across space, it would be absurdly sparse. The observable universe is about 10 to the 27th power cubic meters. That's a 1 followed by 27 zeros cubic meters. The total mass of the observable universe is roughly 10 to the 53rd power kilograms. If we divide the mass by the volume, we get a little average density of about 10 to the 26th power kilograms per cubic meter. To put that in perspective, a cubic mile of space contains, on average, only a few grams of matter. A few grams, in a volume the size of a cubic mile. That's profoundly empty. Space is empty, like profoundly, incomprehensibly empty. The atoms and molecules that make up the matter in the universe are spread out so thin that if you picked a random cubic mile of space, there's probably nothing in it. No stars, no planets, no gas, no dust, just vacuum, just emptiness. The closest stars are light years apart. A light year is about 9 trillion kilometers. The empty space between stars dwarfs the stars themselves. If you traveled from one star to another, you'd spend nearly the entire journey in absolute darkness, seeing nothing, encountering nothing, surrounded by nothing but the endless vacuum of space. Think about this. If you shrank the sun down to the size of a marble, about 1.5 centimeters across, and shrank Earth down proportionally to a grain of sand, the Earth would be separated from the sun marble by about a mile. A mile of empty space separating the sun marble from the Earth grain of sand. Now, the nearest star to the sun would be another marble separated from the sun marble by about 100,000 miles. That's the distance across the United States, roughly. 4 times across the continental United States, with marbles at each end representing the sun and its nearest neighbor. Space is so vast that stars are essentially isolated. They're not in contact. They don't influence each other significantly through direct interaction. They orbit around the center of galaxies, and galaxies orbit within galaxy clusters, but the distances between these objects are enormous. The universe is mostly empty space with little islands of matter separated by vast distances. And yet, this raises a profound question. How can consciousness exist in such an empty universe? How can beings like us, who require complexity, who require atoms arranged in specific ways, who require energy and structure, how can we exist in a universe that's mostly empty? The answer is that while the universe is mostly empty, the regions where matter does collect can become very dense, very complex, very organized. Stars concentrate matter. Planets concentrate matter further. Life concentrates matter even further into intricate arrangements of molecules. We are the universe doing something extraordinary in a tiny corner of itself. And yet, I find myself thinking about scale in another dimension. Time. The universe is old, really old. 13.8 billion years old. 13 billion. That's a longer time than you can really comprehend. Human civilization is about 10,000 years old. Recorded history is about 5,000 years old. A human lifespan is about 70 to 80 years on average, up to maybe 100 or 120 years in exceptional cases. The universe is 1,000,000 times older than recorded human history. It's 100,000 times older than human civilization. It's 100 million times older than a typical human lifespan. In cosmological terms, we might as well not exist in time. We're a blip, a momentary fluctuation, barely registering on the cosmic timeline, and the universe is still expanding. It will continue expanding. Stars will continue burning, fusing hydrogen into heavier elements, converting mass into energy. Eventually, in trillions of years, the last stars will burn out. The universe will be dominated by cold, dead stellar remnants, white dwarfs, neutron stars, black holes. In quadrillions of years, even these will decay or evaporate. Black holes, the most stable objects we know of, will eventually evaporate through Hawking radiation over timescales of 10 to the power of 100 years, a 1 followed by 100 zeros. After all the black holes have evaporated, the universe will reach a state of maximum entropy, where no energy gradients remain and nothing interesting can happen. It'll be a cold, dark, empty expanse of elementary particles scattered across an infinite distance, with unimaginably vast times between any interactions. That's the far future of the universe. That's what awaits trillions of years hence. This process, from Big Bang to heat death, spans an incomprehensible amount of time. By comparison, 13.8 billion years is essentially the beginning. We're living in the earliest era of the universe, when stars are still abundant, when galaxies are still evolving, when complex structures can still form. In a universe that might last 10 to the power of 100 years, we're living in the first instant. This adds another dimension to the question of scale. Not just how big is the universe spatially, but how much time does it have? How much time has already passed? How much time is still to come? When you think about it this way, being alive now, in a universe of stars and galaxies, in a planet capable of supporting life, in an era when stars are still abundant, it's like living at the beginning of an incomprehensibly long story. We're witnessing the opening chapters of a cosmic narrative that will unfold for quadrillions of years after we're gone. But let me return to spatial scale, because I want to explore something that's often overlooked: the structure of the universe at different sizes. We talk about the universe as a singular thing, but it's actually filled with structures of different sizes, nested within each other like Russian dolls. There's you. You're about 2 meters tall. You're surrounded by familiar human scale objects, furniture, buildings, landscapes. You experience the world as a space of meters and tens of meters. Your immediate environment is on this scale. Then there's the Earth. The Earth is 12,742 kilometers in diameter. The Earth is so large that it takes 24 hours to spin once on its axis. It takes a few seconds to speak a sentence, but the Earth spins a measurable distance in that time. It takes hours to drive across a state. It takes days to travel across a continent. The Earth is large relative to you, so large that you've probably never seen more than a tiny fraction of it in one view. Even astronauts in spacecraft see only a portion of the Earth's surface at once. Then there's the solar system. The solar system contains 8 major planets, 1 star at the center, and billions of smaller bodies. The solar system is about 2 light years across. If the Earth were a marble, the solar system would be hundreds of miles across. The Sun is the dominant object, accounting for 99.86% of the mass of the entire solar system. Everything orbits around it. Then there's the Milky Way. The Milky Way is 100,000 light years across and contains 200 billion stars and trillions of planets. If the Sun were a marble, the Milky Way would be enormous, a structure light years across, populated with billions of objects. It would take light 100,000 years to cross it. Then there's the local group of galaxies, a collection of galaxies that includes the Milky Way, Andromeda, and about 80 smaller galaxies. This structure is several million light years across. It's a gravitationally bound system where galaxies orbit each other. Then there's the Virgo supercluster, a massive structure that includes the local group and thousands of other galaxy clusters. This structure is hundreds of millions of light years across. It's the largest known structure in the nearby universe. And beyond that, you have the cosmic web, a vast network of filaments and voids that spans the entire observable universe. Galaxies clump into clusters. Clusters string together into superclusters. Superclusters form long filaments separated by vast voids. The voids are nearly empty of matter, just a few galaxies scattered throughout hundreds of millions of light years of space. Each structure is nested within the next, like Russian dolls, or like concentric circles expanding outward. You are nested inside cities, which are nested inside nations, which are nested inside continents, which are nested inside the Earth, which is nested inside the solar system, which is nested inside the galaxy, which is nested inside the local group, which is nested inside the supercluster, which is nested inside the cosmic web, which is the observable universe. It's dizzying. And at each scale, the size increases by orders of magnitude. Each step outward multiplies the scale by millions or billions or trillions. You go from personal experience, meters, to planetary scale, thousands of kilometers, to solar system scale, billions of kilometers, to interstellar scale, trillions of kilometers, to galactic scale, trillions of kilometers, and beyond. I think about this sometimes. I think about all the structures that contain me. I'm part of all of them in a sense. I'm a local concentration of matter within a human-sized structure, which is within a city, within a nation, within a continent, within a planet, within a solar system, within a galaxy, within a supercluster within the universe. I'm simultaneously an individual and a minute part of vast structures that dwarf me utterly. I'm made of atoms that were forged in the cores of stars billions of years ago. Those stars are part of the Milky Way. The Milky Way is part of the local group. Everything is connected in this nested hierarchy of structures. Everything traces back to the Big Bang, to the initial conditions of the universe, to the fundamental laws of physics. It's both humbling and beautiful. You are impossibly large compared to an atom, about 10 to the 27th power times larger. And you are impossibly small compared to a galaxy, about 10 to the 20th power times smaller. You exist in the narrow band between the quantum world and the cosmic world, in a scale where complexity can emerge and persist. Now, I want to talk about something I find genuinely fascinating: how we know how big the universe is. Because here's the thing, you can't just go out and measure it directly. You can't go to the edge of the universe with a cosmic ruler. You can't send a spacecraft to distant galaxies and have it report back. How do we know these numbers? How can we possibly know the size of something we can't directly access? We know through a combination of observation and inference. We measure what we can and infer what we can't. It's one of the great achievements of science. The ability to determine the properties of distant, inaccessible objects through clever reasoning. The distance to nearby stars we can measure using parallax. The idea is deceptively simple. When Earth is on one side of its orbit around the Sun, a nearby star appears to be in one position relative to background stars. 6 months later, when Earth is on the opposite side of its orbit, the star appears to be in a slightly different position. The star seems to shift against the background. This isn't because the star moved, it's because we moved. It's the same effect you see when you hold your finger up in front of your face and close one eye, then the other. Your finger appears to shift position as you view it from different angles. That's parallax. The amount of apparent movement, the parallax angle, depends on the star's distance. Closer stars shift position more than distant stars. It's a triangle. Earth on one side, the star at the apex, and the background stars on the far side. The farther the star, the narrower the angle. We can measure this shift. If we know the diameter of Earth's orbit, one astronomical unit, which is 150 million kilometers, we can use basic trigonometry to calculate the distance to the star. This works for stars up to a few hundred light years away. Beyond that, the parallax effect becomes too small to measure accurately. The star is so far away that the angle is too narrow to detect with our instruments. For farther galaxies, we use different methods. One is based on something called the cosmic distance ladder, a series of methods that build on each other, each method extending our reach farther into space. For instance, certain stars called Cepheid variables brighten and dim with a regular period. This periodicity is remarkable. The period of brightness variation is directly related to the star's actual luminosity. Brighter Cepheids have longer periods. Dimmer Cepheids have shorter periods. It's a perfect cosmic speedometer. Here's how we use it. First, we find Cepheid variables in nearby galaxies. We measure their apparent brightness from Earth. We know their actual brightness from studying similar Cepheids in our own galaxy using parallax. We compare apparent to actual brightness to determine distance. This allowed Edwin Hubble in the 1920s to measure distances to nearby galaxies and make a revolutionary discovery. The Andromeda Nebula was not part of the Milky Way. It was a separate galaxy, a separate island universe beyond our own. This was perhaps the most profound discovery in cosmology, the realization that the Milky Way is just one galaxy among billions. For even more distant galaxies, we use type 1a supernovae. These are thermonuclear explosions of white dwarf stars in binary systems. A white dwarf pulls material from a companion star until it reaches critical density and temperature, at which point a runaway fusion reaction occurs. Boom! The star explodes. The remarkable thing is that type 1a supernovae all have roughly the same peak brightness. It's like a cosmic standard candle if we know how bright it actually is, and we measure how bright it appears from Earth, we can calculate the distance. This method allowed astronomers to measure distances to billions of light years, opening up the deep universe to measurement. These methods compound. Each method is calibrated using the previous one. It's like measuring the size of a city by first using nearby objects you know the size of, then using objects within the city to measure objects farther away, then using those distant objects to measure even more distant things. Each step builds on the previous, creating a ladder of distance measurements extending into space. We don't directly measure the size of the universe. We infer it from patterns and relationships between things we can measure. And that's remarkable when you think about it. We know the size of the universe, 13.8 billion years old, observable radius of 46 billion light years, containing hundreds of billions of galaxies with hundreds of billions of stars each. Through clever inference from light and mathematical relationships, from the light of Cepheid variables, from the brightness of supernovae, from the redshift of distant galaxies, from the temperature of the cosmic microwave background radiation, we've constructed a detailed picture of the universe's size, age, composition, and fate. We do this all the time in science. We measure what we can and infer what we can't. The precision is surprisingly good. We know the age of the universe to within about 100 million years, a precision of better than 1%. We know the size to similar precision, but there's a limit to what we can know. The observable universe is defined by the cosmic horizon, the farthest we can see given the age of the universe and the speed of light. Beyond that horizon, we can't observe anything, so we can't directly say what's there. The universe might end at that horizon, or it might continue forever. The current evidence suggests it continues, probably infinitely, but we don't know for certain. If the universe is truly infinite, then there's a disturbing and fascinating implication. There are infinitely many galaxies, infinitely many stars, and infinitely many planets. With infinite possibilities, every possible arrangement of matter that could exist probably does exist somewhere out there, infinitely many times. This implies that there are infinitely many copies of you living, infinitely many variations of your life. Somewhere out in the infinite universe, there's a version of you having a different conversation right now, and another version making a different choice, and another choosing differently still. On and on, infinitely. An infinite number of you, living every possible version of your life. This is called the infinite multiverse, or sometimes the cosmic multiverse. It's not a supernatural concept. It's a mathematical consequence of an infinite universe and the finite number of possible arrangements of atoms. Some physicists take this seriously. Others dismiss it as philosophically unsatisfying and potentially unfalsifiable. But the point is, if the universe is infinite, the implications are profound and vertiginous. I find myself oscillating between different feelings when I think about this. On one hand, it's kind of terrifying. You're not unique. Every choice you could make is being made by some version of you. Every life you could live is being lived. Your individual existence becomes statistically insignificant. Your choices don't matter because all possible choices are being made somewhere. On the other hand, it's oddly comforting. If there are infinite versions of you, then there's a version that succeeds, a version that's happy, a version that accomplishes great things, a version that's smarter, faster, stronger, wiser, a version that finds love, another that becomes famous, another that makes profound discoveries. Your potential is infinite because there's a copy of you actualizing every possible version. I don't know which perspective is more true or more useful. Probably both are partially true and partially false. But the thought exercises matter. They change how you think about existence, about choice, about meaning. They invite contemplation about what it means to be unique versus to be insignificant. Now let me try to give you a sense of cosmic scale one more time using a different approach. Let's say you wanted to scale down the observable universe 46 billion light years across to the size of a sphere, 1 meter its diameter, a meter-sized model of everything that exists within our cosmic horizon. What would it look like? Each galaxy would be smaller than a grain of sand. Our entire galactic supercluster, a structure containing thousands of galaxies and millions of light years across, would be a few millimeters across in this model. The Andromeda Galaxy would be a grain of dust, invisible to the naked eye. The Milky Way would also be a grain of dust, invisible to the naked eye. They'd be separated by a few millimeters. Earth would be far, far smaller than any particle your microscope could see. The sun would be smaller still. You would be, well, you wouldn't exist at this scale. You'd be vastly smaller than any physical thing that could exist, smaller than an atom in this model. You'd be non-existent. The universe is so large that if you shrank it down to human scale, every galaxy in it would be too small to see. All the complexity, all the structure, all the phenomena that make the universe interesting, spiral galaxies, black holes, nebulae, star clusters, all of it would be invisible. the entire cosmos squeezed down to a single meter diameter sphere would appear as a featureless, empty ball to the naked eye. That's how big the universe is. Alternatively, let's scale up in the opposite direction. Let's say you magnified an atom to the size of Earth. An atom is roughly 10 to the power of minus 10 meters across. Earth is about 10 to the power of 7 meters across. That's a magnification of about 10 to the power of 17, or 100 quadrillion times larger. At this magnification, a nucleus, the dense core of an atom, would be as big as a large building. An electron, the negatively charged particle that orbits the nucleus, would be, well, electrons don't have a defined size in the classical sense, but if we treated them as point particles, they'd be infinitesimally small, even at this magnification. A person would be enormously large. You'd be larger than the solar system. You'd be hundreds of times larger than the distance to Neptune. You'd dwarf galaxies in linear extent. This is the inverse problem. The universe is so large that atoms are incredibly small by comparison. The ratio of your size to an atom is comparable to the ratio of a galaxy to your size. When I think about scale this way, I'm struck by how much structure exists between atoms and galaxies. There are many orders of magnitude of size, each with its own complexity and phenomena. Atoms exist at the quantum scale, governed by quantum mechanics. Molecules are slightly larger, composed of atoms bonded together. Cells are larger still, composed of molecules organized in specific ways. Organisms are collections of cells. Ecosystems are collections of organisms. Planets are the homes of ecosystems. Stars are the power sources for planetary systems. Galaxies are vast collections of stars. And the observable universe is a vast collection of galaxies. But in some sense, we're not halfway between atoms and galaxies in size. We're much, much closer to atoms than to galaxies. The atoms in your body are only about 10 to the power of minus 10 meters smaller than you are. But galaxies are about 10 to the power of 20 meters larger than you are. The ratio is vastly different, about 1,000,000 to 1. You're much, much closer in scale to an atom than to a galaxy. In cosmic terms, you're practically an atom yourself, just an atom made up of many smaller atoms arranged in a particular way. I find this oddly humbling. I think of myself as substantial, as real, as taking up space. But relative to a galaxy, I'm barely anything at all. I'm a tiny temporary arrangement of atoms, conscious for a brief moment in cosmic time, aware of vast structures that dwarf me utterly. And yet, the universe is vast enough that there are places in it where I exist, where you exist, where consciousness exists. That same vastness that makes me insignificant is also what makes me possible. If the universe were smaller, if there were fewer resources, fewer stars, fewer planets, complex structures like us might never have formed. The universe has to be large enough to support the emergence of complexity and consciousness. The size of the universe and the existence of creatures that can comprehend that size are deeply intertwined. I think about this a lot. I think about my 8-year-old self lying in that field, feeling like I was going to fall off the earth because I suddenly grasped some inkling of cosmic scale. I think about how that feeling has evolved over years into something more nuanced, a kind of appreciation mixed with awe and humility. The universe is vast, incomprehensibly vast, but it's also knowable. We can measure it. We can understand it. We can develop intuition for how large it is, even though our minds aren't naturally equipped to handle those scales. This ability To transcend the limits of our intuition and reach toward genuine understanding of something beyond our experience might be one of the most important things consciousness is capable of. We're small, we're insignificant relative to the cosmic scale, but we're conscious. We can think, we can measure, we can understand. We can look at light that's been traveling toward us for billions of years and extract meaning from it. We can build models of the universe, calculate its properties, infer its structure and history. That's extraordinary. That's remarkable. That's something that shouldn't be taken for granted. Now, I want to address something that comes up when people think about cosmic scale, the question of whether there's anything special about the location where we are. This is called the Copernican principle. It's the idea that we don't occupy a special or privileged location in the universe. The Earth orbits an ordinary star, in an ordinary galaxy, in an ordinary location in the cosmic web. This was revolutionary when it was first proposed. For most of human history, we assumed the opposite. We assumed Earth was at the center of everything. The sun orbited us. The stars were on a celestial sphere around us. We were special. We were the center of creation. Copernicus and later astronomers showed that we orbit the sun, not the other way around. Later, astronomers showed that the sun is just one of billions of stars. Hubble showed that galaxies exist beyond the Milky Way. Cosmologists showed that we're not at the center of the universe. We're distributed throughout a cosmic web where some places have more matter and others have less. But there's no cosmic center, no special location where everything orbits around us. The Copernican principle became central to our worldview. We are not special. Our location is ordinary. Our solar system is ordinary. Our galaxy is ordinary. We're just one of countless observers scattered throughout an indifferent universe. But I want to push back on this a little bit, not to contradict the Copernican principle, but to add nuance to it. Yes, we occupy an ordinary location in the universe. Yes, our solar system is ordinary. Yes, our galaxy is ordinary. Not particularly large, not particularly small. Yes, our position in the cosmic web is unremarkable. But here's the thing. We're one of the only known places in the universe where complex structures like consciousness have emerged. We're rare. Maybe not unique, but rare. The universe is vast enough that the probability of life emerging on a given planet is extremely low. But there are so many planets, maybe 10 to the 24th power planets in the observable universe, that even an extremely low probability becomes certainty somewhere. But consciousness, intelligent life, civilizations capable of building telescopes and doing mathematics and inferring the structure of the cosmos itself, that might be much, much rarer. It might be that we are, in fact, unique. Or if not unique, then a vanishingly small minority of conscious beings in the universe. If that's true, then our ordinariness is shadowed by our rarity. We're ordinary spatially, but extraordinary in being aware of that ordinariness. We're conscious observers of an unconscious universe. We're the universe reflecting on itself. This isn't special in the way earlier humans thought it was special. God isn't watching us because we're at the center of everything, but we might be special in a different way. We might be conscious observers in a universe that is, as far as we know, mostly unconscious. That's a kind of privilege, even if it's not the kind our ancestors imagined. I think about this sometimes when I'm looking at the night sky. I think about the fact that most of those stars will never be observed by any conscious being. They'll shine for billions of years, their light spreading into the universe, perhaps surrounded by planets, perhaps even with life on those planets. And yet, no one will ever truly know about them. But those stars that we do observe, we know about. We've studied them, we've named them, we've written about them. They exist in human consciousness as well as in physical space. That's a kind of immortality, I suppose. Being observed, being known, existing not just physically, but also in the minds and memories of other conscious beings. When I look at the night sky, I'm connected to those stars. The light from them has traveled for years, or decades, or millions of years to reach my eye. I'm literally seeing the past. The light that reaches me carries information about what those stars were like in the past. This is what Carl Sagan meant when he talked about being made of star stuff. The atoms in my body were forged in the cores of stars billions of years ago. The carbon in my cells, the oxygen, the iron, the calcium, all of it came from stars that lived and died before the solar system formed. Stars exploded as supernovae, scattering their material across space. Some of that material coalesced into the cloud that formed our solar system. Some of it became Earth. Some of it became the atoms that make up my body and mind. I'm not just observing the universe, I'm part of it. I'm made of it. The universe is observing itself through my eyes. The universe has become conscious, at least in this one small corner, and is contemplating its own vastness. That's pretty profound if you think about it. Now, I want to circle back to something I mentioned earlier, the expansion of the universe. This is a key feature of cosmic scale that I want to explore more deeply. When we observe distant galaxies, we see that they're moving away from us. The farther away they are, the faster they're moving. This is called the Hubble expansion, named after Edwin Hubble, who discovered it in the 1920s. This might initially seem strange. Why would distant galaxies be receding from us? It would be natural to think that the universe has an edge somewhere, and everything is fleeing from that edge. Or that the galaxies are moving through space like shrapnel from an explosion. But neither of those is correct. The Hubble expansion doesn't mean galaxies are moving through space away from us. It means that space itself is expanding. The distance between galaxies is increasing, not because they're moving through space, but because there's more space being created between them. Think of it like a raisin cake baking in an oven. As the cake rises, as it expands, the raisins embedded in it get farther apart from each other. The raisins aren't moving through the cake is expanding. Similarly, the universe is expanding. The fabric of space itself is expanding. This expansion means that the distance between all galaxies is increasing. It's happening everywhere simultaneously. There's no center to the expansion, no point from which everything is flying outward. Every galaxy sees every other galaxy receding from it. If we run this expansion backward through time, at some point in the past, all the galaxies must have been closer together. Run it back farther, and they were even closer. Run it all the way back, and all the matter in the universe was compressed into an incredibly dense, incredibly hot state, a singularity. That was the Big Bang. The Big Bang wasn't an explosion in space. It was an expansion of space itself. There was no location where the Big Bang happened. It happened everywhere simultaneously, throughout all of space. And before the Big Bang, there was no before. Space and time didn't exist before the Big Bang. The Big Bang was the creation of space and time itself. This concept is mind-bending. Our intuition fails us here. We're used to thinking about events happening in space and time, but the Big Bang was the creation of space and time. It's not an event that happened somewhere. It was the beginning of somewhere-ness itself. Asking what came before the Big Bang is like asking what's north of the North Pole. The question itself doesn't make sense. North is a direction relative to the Earth's geography. Northward from the North Pole doesn't exist. There's no farther north. Similarly, before is a concept relative to time. Before the Big Bang, there was no time, so before doesn't apply. The Big Bang created space, time, and all the matter and energy in the universe. Everything we see, everything we are, emerged from that initial expansion. Galaxies condensed from the primordial gas. Stars formed within galaxies. Planets formed around stars. Life emerged on suitable planets. Consciousness emerged in some places, allowing the universe to contemplate itself. 13.8 billion years later, the universe is still expanding. Galaxies are still receding from each other. The expansion is happening at every location in the universe, not from a center outward. It's the very fabric of space growing, stretching, becoming larger. And here's something that fascinates me. The expansion might not slow down. For decades after the Big Bang was first proposed, cosmologists thought gravity would eventually slow down the expansion. They thought the mutual gravitational attraction of all the galaxies would eventually overcome the initial momentum of the Big Bang and pull all the galaxies back together in a catastrophic big crunch. But observations in the 1990s showed something unexpected. The expansion is accelerating. Distant galaxies are receding faster than we'd expect based on the initial expansion rate. Something is pushing the universe apart, counteracting gravity. We don't know what this something is. We call it dark energy, which is really just a name for the phenomenon we don't understand. Dark energy comprises about 68% of the universe's energy. We know it exists because of its gravitational effects on galaxies and the cosmic microwave background radiation. But we don't know what it is. It might be a property of space itself. It might be some particle or field we haven't discovered. It remains one of the deepest mysteries of physics. The implication is that the universe will probably expand forever. Galaxies will continue receding. Eventually, all the stars will burn out. All the black holes will evaporate through Hawking radiation over timescales of 10 to the power of 100 years. The universe will reach maximum entropy, a state where no energy gradients remain, where no work can be done, where nothing interesting can happen. It'll be a cold, dark, empty expanse of elementary particles scattered across an infinite distance, with unimaginably vast times between any interactions. That's the far future of the universe. It's depressing in a way, this vision of a universe that started with the Big Bang, created complexity and beauty and consciousness, and then over incomprehensible timescales will decay into an empty void. But it's also oddly liberating. We're living in the brief moment when stars exist, when complexity can form, when life is possible, when consciousness can emerge and marvel at the universe. In cosmic terms, we're living in a golden age. We're living at a time when the universe is still young enough that stars shine brightly, when galaxies are still evolving, when the emergence of new structures is still possible. If the universe exists for 10 to the power of 100 years from beginning to end, we're living in the first instant. We're at the very beginning of a story that will unfold for trillions of years after we're gone. And yet we're here now, conscious, aware, capable of understanding our cosmos. That's remarkable. There's one more dimension to cosmic scale I want to explore: the relationship between distance and time. When astronomers say a galaxy is 1 billion light years away, they're making a statement about both space and time. The light from that galaxy has been traveling toward us for 1 billion years. When we observe it through a telescope, we're not seeing that galaxy as it exists today. We're seeing it as it existed 1 billion years ago. This has profound implications. It means that by looking at distant galaxies, we're actually looking backward in time. We're seeing the history of the universe written in the sky. The Hubble Space Telescope has imaged galaxies so distant that their light has been traveling toward us for more than 13 billion years. These are galaxies we're seeing as they appeared when the universe was less than 1 billion years old. We're seeing the universe in its youth. This is one of the most remarkable achievements of observational astronomy, that by simply looking far enough away, we can look back in time to when galaxies were first forming, when the universe was young and radically different from today. I find this perspective deeply moving. Every photograph of the distant universe is a window into the past. Every deep field image from Hubble, showing thousands of galaxies in a tiny patch of sky, is a historical document showing us what the universe looked like billions of years ago. Now let me return to the scale of individual human perception and how it relates to cosmic scale. We often talk about humans being insignificant in the universe, and in some sense, that's absolutely true. Compared to galaxies, compared to cosmic structures, we are vanishingly small. Our planet is a grain of sand. Our solar system is an invisible speck. Our galaxy is one of billions. And yet, there's something profound about our place in the cosmic hierarchy. We exist in that narrow band of scale where complexity can emerge and sustain itself. We're large enough to be complex, but small enough to fit within a planet. We're made of atoms, but organized into patterns that can think and reason and wonder. This Goldilocks position in the hierarchy of scales, not too large, not too small, is a prerequisite for our existence. A universe that was too small might never develop the complexity needed for life. A universe that was vastly larger might never develop conscious observers. The universe appears to be precisely calibrated for the emergence of complexity and consciousness. Physicists call this the anthropic principle, the observation that the universe must have properties compatible with the existence of conscious observers, because otherwise there would be no one around to observe it. This doesn't mean the universe was designed for us. It just means that we necessarily find ourselves in a region of the universe and a time in cosmic history where the conditions are right for our existence. Another way to think about cosmic scale is through the lens of probability and rarity. Given the vast size of the universe, how rare are phenomena like Earth, life, and consciousness? Let's start with Earth. There are an estimated 10 to the 24th power planets in the observable universe. That's a septillion planets. Earth is one of them. If planets with liquid water and a stable orbit are genuinely rare, then Earth becomes more special. We don't yet know how common Earth-like planets are. Early observations from the Kepler Space Telescope suggest that many stars have planets, and that Earth-like planets might be fairly common. But common in cosmic terms still means rare. From a human perspective, life might be even rarer. If only 1 in 1 billion planets develops life, then even with 10 to the 24th power planets, there would be 10 to the 15th power biospheres in the observable universe. That's still an enormous number, but it means life isn't randomly scattered throughout space. It would be clustered around certain types of stars, in certain regions of galaxies. Consciousness is likely much rarer still. If only 1 in 1 trillion biospheres produces conscious observers, then the number of conscious civilizations in the observable universe might be countable on our fingers. This is related to the Fermi paradox. The observation that despite the vast number of stars and planets, we haven't detected any obvious signs of alien civilizations. Where are they? The sobering answer might be that consciousness is genuinely rare. Perhaps we are one of only a handful of conscious civilizations in the entire observable universe. Perhaps we are, in fact, unique. This perspective inverts our sense of scale. We're made insignificant by the size of the universe, but made significant by the apparent rarity of consciousness within that vastness. Let me also explore the concept of cosmic distances and their implications for travel and communication. The nearest star system, Alpha Centauri, is 4.37 light years away. If we sent our fastest spacecraft, it would take approximately 80,000 years to reach Alpha Centauri. That's 80 times longer than the entire span of human civilization so far. Interstellar travel, as envisioned in science fiction, runs headlong into these cosmic distances, even traveling at close to the speed of light, which current physics suggests is impossible for massive objects. A journey to the nearest star would take years. A journey to the galactic center would take tens of thousands of years. These timescales exceed any realistic human planning horizon. They challenge our sense of agency and our ability to explore and colonize space. And yet, they also illuminate why space might be our future. On a cosmic timescale of billions of years, even these vast distances become traversable. A civilization that lasts for 1 billion years could, in principle, spread throughout the galaxy. A civilization that lasts for 1 trillion years could potentially spread throughout the observable universe. But the universe is also expanding. The farther away a galaxy is, the faster it's receding due to cosmic expansion. Some galaxies are receding so fast that light from them will never reach us. The cosmological horizon, the boundary of the observable universe, is itself expanding and moving away from us. This means that the universe is becoming progressively less observable to us. Galaxies that we can see today will eventually recede beyond the cosmic horizon. In the far future, observers in any given region will be able to see only their local cluster of galaxies. The broader cosmic structure will become invisible. This is a sobering thought for anyone hoping for future civilizations to map and explore the entire universe. The cosmos is not just large, it's actively escaping observation as it expands. Another aspect of cosmic scale worth contemplating is the distribution of matter and energy in the universe. We've mentioned that space is mostly empty, but there's a structure to how matter is distributed. Galaxies are not randomly scattered. They cluster into groups and clusters, which themselves cluster into superclusters. The largest structures known are filaments of galaxies separated by vast voids containing almost no matter. This structure tells us something important. The universe isn't homogeneous at small scales. Look at any tiny patch of space and you'll find it's part of a larger structure. But zoom out far enough and the universe does appear homogeneous, similar density and structure in all directions. This is called the cosmological principle. The cosmic web, the large-scale structure of galaxies and filaments, is one of the most complex structures in the universe. It formed due to gravity acting on tiny density fluctuations in the early universe. Over billions of years, gravity amplified these fluctuations, pulling matter together into galaxies and clusters. We are embedded within this structure. Our solar system is part of the Milky Way, which is part of the Local Group, which is part of the Virgo supercluster, which is part of a larger filament in the cosmic web. Understanding our place in this hierarchy Realizing that we're part of increasingly larger structures at each scale helps create perspective. We're not isolated points in a uniform void. We're part of a vast interconnected structure that spans billions of light years. Finally, I want to return to the personal and philosophical dimensions of understanding cosmic scale. When we grasp, really grasp, how large the universe is, how far away things are, how much time has passed, and how much time remains, something shifts in our perspective. Ordinary concerns can seem trivial. Social conflicts, career ambitions, personal grievances, they all shrink when placed against the backdrop of cosmic scale. But this can be either depressing or liberating, depending on your perspective. Depressing. Nothing I do matters because the universe is incomprehensibly large and I'm incomprehensibly small. I'll be dead in 80 years and the universe will continue for trillions of years. My life is meaningless. Liberating. The universe is beautiful and vast, and I have the privilege of being conscious within it. I can contemplate its structure, marvel at its scale, understand how it works. I'm made of star stuff, created by the universe to observe and understand itself. That's extraordinary. Both perspectives are based on the same facts. The difference is in how you choose to interpret those facts. For myself, I find contemplating cosmic scale to be a genuinely spiritual exercise, even though I don't use the term spiritual in any religious sense. It creates a kind of awe and humility. It reminds me that my problems, while real and important to me, exist within a much larger context. It also creates a sense of kinship with all conscious observers. If there are other civilizations out there, and the sheer size of the universe suggests there might be, then we share something profound, the ability to contemplate existence. We're all observers of the universe, trying to understand our place within it, wondering if we're alone. When I look at the night sky now as an adult, I feel something different than that 8-year-old vertigo I experienced in the field. I feel a sense of connection. The light reaching my eyes has traveled through vast distances, through billions of years of cosmic history, and has finally arrived to be observed by this conscious being. Every photon carries information about the universe. Every star I see is actually a nuclear furnace, fusing hydrogen into heavier elements, creating the building blocks of planets and life. Every galaxy I see contains billions of stars and trillions of planets. I'm not just looking at the sky, I'm looking at a vast symphony of processes operating simultaneously across billions of light years. I'm seeing the universe as it was in the past. I'm connected to all the matter in the cosmos through shared origin in the Big Bang. That's not insignificant. That's remarkable. So, to return to the original question, how big is the universe? The answer is that it's incomprehensibly, unimaginably vast. But that vastness is also knowable. We can measure it. We can understand it. We can fit it into our minds, even if we can't fit it into our intuition. And in doing so, we transcend the limitations of our evolved perception and reach toward genuine understanding of something beyond our immediate experience. We become, in a real sense, cosmic observers. We participate in the universe's self-understanding. That's what it means to be conscious in this vast cosmos. Let me explore one more dimension of cosmic scale that often gets overlooked: the observable universe boundary and what lies beyond. The observable universe has a radius of about 46 billion light years. This is the distance at which we can see the most distant galaxies given the current age of the universe and the expansion of space. But the observable universe is not the edge of the universe. It's the edge of what we can observe from our current location at this current time. Imagine standing in a fog so thick you can only see 100 meters in any direction. Everything beyond 100 meters is invisible to you. You might conclude that the world is only 200 meters across, but that would be wrong. The world extends far beyond what you can see. Your inability to see farther doesn't mean there's nothing there. You're just limited by the fog. The cosmic microwave background radiation is our fog. It's the oldest light in the universe, created about 380,000 years after the Big Bang, when the universe became transparent. We can't see any farther back than this radiation because the earlier universe was opaque. The cosmic horizon, the edge of the observable universe, is defined by this limit. Beyond it, there's likely more universe, more galaxies, more structure. But we can never see it because light from beyond the horizon hasn't had time to reach us. This is deeply humbling. Our entire cosmic perspective, everything we know about the universe, is based on observations from a bubble 46 billion light years in radius. Beyond that bubble, there might be regions of space so vast that our entire observable universe would appear as an insignificant speck. Current theory suggests the universe is much larger than the observable universe. It might be infinite. If it is infinite, then there are infinite stars, infinite galaxies, infinite possibilities. An infinite universe raises philosophical questions that have occupied thinkers for centuries. If space is infinite, then perhaps everything that could exist does exist. Somewhere out in the infinite cosmos, there might be perfect duplicates of this planet, with a duplicate of you living a duplicate of your life. There might be copies where things went slightly differently, copies where things went radically differently. This is sometimes called the many worlds interpretation of quantum mechanics applied to cosmology. The idea that the entire quantum wave function of the universe has been realized somewhere in infinite variations. It's simultaneously profound and disturbing. On one hand, it means your potential is infinite. Every choice you could make is being made. Every life you could live is being lived. On the other hand, it means your individual choices don't matter. They're already all being made. Now let me explore the role of dark energy and dark matter in cosmic scale. Ordinary matter, the stuff we're made of, the stuff that makes up stars and planets and galaxies, comprises only about 5% of the universe's total energy content. Weird, right? The rest is made up of dark matter, about 27%, and dark energy, about 68%. Dark matter is called dark because it doesn't interact with light. It's invisible. We know it exists because of its gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Something invisible must be providing additional gravitational attraction. That something is dark matter. Dark matter might be WIMPs, weakly interacting massive particles, or axions, or some other exotic particle we haven't discovered yet. We've built elaborate experiments to detect dark matter, but so far we haven't definitively caught any. Dark matter fills the space between and within galaxies. There might be 5 to 6 times as much dark matter as ordinary matter. You're surrounded by dark matter right now, but you'll never feel it or see it. It passes through you without interacting. Dark energy is even more mysterious. It comprises the majority of the universe's energy, and yet we have no idea what it is. We only know it exists because observations show the expansion of the universe is accelerating. Dark energy might be a property of space itself, a kind of vacuum energy intrinsic to empty space. As space expands, more empty space is created, and if empty space has energy, then the total dark energy increases. This creates a repulsive gravitational effect that accelerates expansion. Alternatively, dark energy might be some exotic form of matter we haven't discovered, or it might be a failure of our understanding of gravity at cosmic scales. The bottom line, 95% of the universe is made of things we don't understand. We know the universe's composition intimately in some ways. We understand stars, planets, chemistry, but we're ignorant of its dominant components. This is humbling. Despite all our sophisticated astronomy and physics, we're missing 95% of the universe. It's like trying to understand an ecosystem while being blind to 95% of its biomass. We're working with incomplete information. Let me also explore what life might look like across cosmic scales. If life emerges at a certain probability rate, and there are 10 to the 24th power planets in the observable universe, then the total number of biospheres could be enormous. Let's say conservatively that 1 in a trillion planets develops life. That would give us 10 to the 12th power biospheres, a trillion habitable worlds, a trillion worlds with life, just in the observable universe. The sheer diversity would be staggering. Life might emerge in radically different environments than Earth: subsurface oceans on ice moons, the atmospheres of gas giants, clouds of organic molecules around cool stars. Life in forms we can barely imagine, not carbon based, not DNA based, not chemical based at all. And if life emerges on a trillion worlds, how many of those worlds develop intelligence? Consciousness? We don't know the probability. Intelligence might be extremely common, a natural outcome of evolution whenever conditions allow, or it might be vanishingly rare, a fluke that happened once or twice in the entire observable universe. The Fermi paradox, where is everybody, suggests intelligence might be rare. We've pointed our telescopes at the sky, listened for radio signals, searched for technosignatures. We've found nothing. There are various explanations. Maybe intelligent life self-destructs before spreading. Maybe it's far rarer than we think. Maybe they're deliberately hiding from us. Maybe civilizations don't use radio anymore and we're looking for the wrong signals. Maybe we're early, first on the scene in our region of the universe. Or maybe we really are alone, or among the very few conscious civilizations in the observable universe. The cosmic perspective can feel lonely. Billions of galaxies, billions of stars per galaxy, but possibly no one listening, no one else thinking about the stars, no one else wondering if they're alone. And yet, the sheer numbers suggest we shouldn't give up hope. Somewhere statistically, other observers might exist, other conscious minds contemplating their place in the cosmos, just as we do. Let me explore one more concept related to cosmic scale: the arrow of time. The universe has a direction in time. Things move from low entropy, ordered, to high entropy, disordered. This is the second law of thermodynamics, and it's one of the most fundamental laws of physics. The Big Bang represented a state of extremely low entropy, all matter and energy compressed into an incredibly ordered configuration. The universe has been expanding and becoming more disordered ever since. Eventually, the universe will reach maximum entropy, a state where everything is homogeneous and cold, with no energy gradients that could drive interesting processes. This defines the arrow of time. The future is the direction of increasing entropy. The past is the direction of decreasing entropy. The Big Bang is the ultimate past. The heat death is the ultimate future. We experience time as flowing from past to future. We remember the past, but not the future. We can influence the future, but not the past. These asymmetries all trace back to the increase of entropy. The cosmos is moving from an incredibly ordered beginning to a completely disordered end. We live in the first moment of this long journey, when stars still shine and complexity still exists. This perspective adds weight to the question, how big is the universe? Not just in space, but in time. Not just how many galaxies, but how much history is ahead of us. Not just how far we can see, but how far future observers will be able to see as the universe expands and galaxies recede beyond the horizon. Finally, let me return to where this entire journey began, with that 8-year-old boy lying in a field, struck by cosmic vertigo. That vertigo, that feeling of falling into infinity, is, I think, one of the most authentic responses to cosmic scale. It's what happens when your mind briefly glimpses something so vast that your usual sense of scale collapses. As we grow older and learn about the universe, we can recover from that vertigo. We can develop conceptual frameworks that make the incomprehensible comprehensible. We can fit the size of the universe into our minds, even if we can't fit it into our intuition. But something is lost in that translation from feeling to understanding. The raw awe, the genuine wonder, the vertigo itself, it can fade as understanding replaces incomprehension. I think it's important to preserve that sense of awe, even as we develop understanding. The universe really is that large. The distances really are that vast. Our scale really is that small. And that's okay. It's not depressing or lonely unless we make it so. Instead, we can choose to find meaning in our smallness. We can marvel at the fact that we exist at all in this vast cosmos. We can appreciate that we're able to understand it, to do science, to build telescopes and probe deeper and deeper into space and time. We're part of the universe. We're made of its matter, energized by its fundamental forces, evolved through its evolutionary processes. The same forces that created galaxies created us. And that, I think, is remarkable. The universe is incomprehensibly large, and we are incomprehensibly small relative to it. But we're here, conscious, aware, capable of understanding the cosmos. That's the most remarkable thing of all. Let me spend some time on a topic that relates directly to cosmic scale, the history of how we learned these distances. For most of human history, we didn't know how far away the stars were. We assumed they were on a celestial sphere, all at the same distance, just at different positions. The idea that some stars might be farther than others wasn't even considered. The Greek astronomer Hipparchus, working around 150 BCE, tried to measure the distance to the Sun using parallax. His method was sound, but his measurement tools weren't precise enough. He concluded the Sun was much farther away than it actually is, but at least he had the right idea. It wasn't until the 18th century that parallax measurements became precise enough to work. As Earth orbited the Sun, nearby stars seemed to shift position slightly relative to distant stars. By measuring this shift and doing trigonometry, astronomers could finally calculate stellar distances. But the distances were enormous. They were so large that a new unit of measurement was needed. The light year, the distance light travels in a year, became the standard unit for cosmic distances. When the first stellar distances were measured, it was shocking. The nearest star, Proxima Centauri, was 4.24 light years away. This meant light from that star took over 4 years to reach Earth. The implications were staggering. Then, in the early 20th century, Edwin Hubble made an even more shocking discovery. He measured the distance to the Andromeda galaxy and found it was 2 million light years away, far beyond the Milky Way. This revealed that the Milky Way was just one galaxy among many. This was revolutionary. Overnight, our conception of the universe expanded by a factor of millions. What we thought was the entire universe, the Milky Way, turned out to be just one galaxy in a vast cosmos. Since then, our measurements of cosmic distance have improved. The Hubble Space Telescope, launched in 1990, revolutionized distance measurements again, allowing us to see deeper into space and measure distances to the most remote galaxies. Current technology allows us to see galaxies so distant their light has been traveling for over 13 billion years. We're looking at the universe as it was when it was very young. Future telescopes will allow us to see even farther. The James Webb Space Telescope, launched in 2021, can see even more distant galaxies than Hubble. The extremely large telescope, currently under construction, will be even more powerful. As our technology improves, our cosmic perspective expands. We see farther, we measure more accurately, we understand more deeply. But each advance also reveals how much we don't know. The universe continues to surprise us. Now let me explore the concept of cosmic expansion in more detail. The expansion of space isn't like an explosion where objects fly apart through empty space. It's more fundamental than that. The space itself between objects is increasing. New space is being created. Think of a balloon with dots painted on it. As the balloon inflates, the dots get farther apart. The dots aren't moving through the balloon. The balloon itself is expanding. Similarly, galaxies aren't moving through space. Space itself is expanding. This expansion has profound implications. Observers in different galaxies will disagree about cosmic distances because space is expanding. An observer in the Andromeda galaxy will measure distances to other galaxies differently than we do because space is expanding differently in their region. There is no absolute reference frame in the universe. There is no privileged location from which cosmic distances are measured. Everything is relative to the observer. This relates to Einstein's theory of relativity. Space and time aren't absolute, they're relative. Different observers in different reference frames will measure space and time differently. At cosmic speeds, approaching the speed of light, relativistic effects become important. Time dilation means that time passes more slowly for fast-moving objects. Space contraction means that moving objects appear shortened in the direction of motion. These effects aren't just theoretical. Particles created in the upper atmosphere by cosmic rays demonstrate these effects every day. Muons created by cosmic rays should decay before reaching Earth's surface based on their lifespan in their rest frame. But because they're moving at relativistic speeds, time passes slowly for them. They last long enough to reach Earth before decaying. Relativity also means that gravity is the curvature of space-time. Massive objects like stars and black holes curve the space-time around them. Objects moving through curved space-time follow curved paths, which we perceive as gravitational attraction. At cosmic scales, this curvature of space-time becomes important. The universe itself is curved, whether it's positively curved, like a sphere, negatively curved, like a saddle, or flat, Euclidean, is an open question that astronomers are trying to determine through careful measurements. The curvature of space-time at cosmic scales affects how distances are measured, how light travels, how the universe expands. It's a beautiful connection between the small scale physics of relativity and the large scale structure of the universe. Let me also discuss what cosmic scale means for the future of humanity. If we want to reach other star systems, we face the challenge of vast distances and the limitations of relativity. The nearest star is 4.24 light years away. Even with a spacecraft traveling at 10% the speed of light, far beyond our current capabilities, it would take over 40 years to arrive. Reaching the galactic center, about 26,000 light years away, would require hundreds of thousands of years at current speeds. These timescales challenge our sense of what's possible, but they also define an ambition for future generations. Perhaps someday, thousands or millions of years in the future, humanity or its descendants will have the capability and desire to spread throughout the galaxy. Perhaps consciousness, having emerged in this corner of the universe, will eventually populate other corners. Cosmic scale provides both a limitation and a motivation. It's a limitation because the distances are so vast. It's a motivation because the potential is enormous. A galaxy contains billions of stars and potentially trillions of planets. If consciousness can spread throughout a galaxy, it could flourish on an unimaginably vast stage. And the universe contains billions of galaxies. If consciousness spreads beyond our galaxy, the potential expands exponentially. These are far future considerations, but they're grounded in understanding cosmic scale, understanding how large the cosmos is, and what that means for the distribution of matter and possibilities. Let me reflect on one more aspect of cosmic scale: the role of probability and selection effects. We exist on Earth, orbiting the Sun in the Milky Way. We might wonder, how typical is our location? How typical is our situation? By most measures, we're quite ordinary. The Sun is an average star, not particularly large or small, not particularly old or young. Earth is roughly Earth-sized. Our galaxy is a large spiral galaxy, but not unusually large. Yet we're here, conscious, alive. We exist. This is sometimes called the selection effect or the observer selection principle. We can only observe locations where observers like us can exist. We couldn't exist in the depths of a black hole, so we don't observe black holes from the inside. We couldn't exist in the early universe before atoms formed, so we don't observe that era directly. This creates a bias in what we observe. We observe locations compatible with our existence. We're guaranteed to be in a location where complex life can emerge, because only in such locations can we exist to make observations. This doesn't mean we're special or chosen. It just means we're biased observers. We're guaranteed to observe ourselves in compatible locations. This principle has implications for how we interpret our observations. If we find Earth-like planets are rare, we might conclude life is rare. But if we account for the observer selection effect, that we're guaranteed to be in a habitable location, then rare Earth-like planets is entirely consistent with a universe full of life in exotic locations. Finally, let me return to that 8-year-old me, lying in a field, struck by the vertigo of cosmic scale. If I could speak to that child now, what would I say? I think I'd say, you felt something real. That vertigo you experienced is a genuine response to genuine vastness. The universe really is that large. The stars really are that far away. And yes, you're incredibly small in comparison. But that's not depressing. It's wonderful. As you grow up, you'll learn more about the universe. You'll learn numbers and measurements and physics. You'll understand better how it all works. But don't let understanding chase away the wonder. The universe is no less amazing for being understood. If anything, it becomes more amazing. You'll find that being conscious in a vast universe is a gift. You'll be able to think thoughts no other animal on this planet can think. You'll be able to understand concepts that your ancestors couldn't imagine. You'll be part of a long chain of beings stretching back to the Big Bang, all attempting to understand the cosmos. The universe is 13.8 billion years old. It's 46 billion light years across. It contains billions of galaxies, each with billions of stars. Most of it is empty space. You are incomprehensibly small compared to all this. And you're here now, able to contemplate it. That's remarkable. The universe is large beyond intuition, but it's knowable, understandable, comprehensible to minds like ours. We can measure it, calculate it, build models of how it works. And in doing so, we transcend the limitations of our evolved perception. We become cosmic observers, understanding our place in a vast and beautiful cosmos. That's what it means to understand how big the universe is. I want to explore one specific cosmic phenomenon that really illustrates scale in a concrete way: black holes. Black holes are regions of space where gravity is so strong that not even light can escape. They're created when massive stars collapse at the end of their lives. The largest black holes we know of are supermassive black holes at the centers of galaxies. These can have masses billions of times that of the Sun. The supermassive black hole at the center of the Milky Way, called Sagittarius A star, has a mass of about 4 million solar masses. Let me put that in perspective. The Sun has a mass of about 2 times, cus 10 to the power of 30 kilograms. Sagittarius A star has a mass of 4 million times that, about 8 times 10 to the power of 36 kilograms. This enormous mass is compressed into a region not much larger than Earth's orbit around the Sun. The density is inconceivable. A teaspoon of black hole material would weigh as much as all the mountains on Earth. Black holes curve space-time so severely that they create regions from which nothing can escape. The event horizon. The radius of this region, the Schwarzschild radius, is proportional to the black hole's mass. For a black hole with the mass of Sagittarius A star, the event horizon would be about 44 million kilometers in radius. That's roughly the distance from Earth to the Sun. An entire region of space the size of Earth's orbit. Nothing can escape from inside this region. If you fell past the event horizon, you couldn't send signals out. You couldn't return. You'd be trapped in the black hole forever, experiencing tidal forces that would eventually stretch you into spaghetti as you approach the singularity. Black holes are some of the most extreme objects in the universe, and their existence is a consequence of relativity operating on truly cosmic scales. Now let me explore neutron stars, which are almost equally extreme in different ways. When a massive star explodes as a supernova, the core can collapse into a neutron star. A neutron star is so dense that all its electrons have been forced into its protons, creating neutrons. A typical neutron star has a mass comparable to the Sun, but compressed into a sphere only about 20 kilometers in radius. The density is almost incomprehensible. A teaspoon of neutron star material would weigh about 1 billion tons. The gravitational field on the surface of a neutron star is intense. If you were standing on a neutron star, you wouldn't survive for long. You'd experience acceleration of about 200 billion times Earth's gravity. Any atoms in your body would be crushed instantly. Some neutron stars rotate rapidly, sending beams of radiation toward us as they spin. These are called pulsars. They spin so fast, up to hundreds of times per second, that they're among the most precise clocks in the universe. Pulsar timing is so accurate that astronomers have used it to detect gravitational waves. Neutron stars and black holes represent the extreme states of matter that exist in the universe. They're laboratories where physics operates under conditions we can't recreate on Earth. Studying them reveals how matter and space-time behave in these extreme regimes. Let me also explore what we know about the very early universe close to the Big Bang. The universe began as an infinitely hot, infinitely dense singularity. Immediately after the Big Bang, the universe was dominated by radiation, extremely high energy photons bouncing around in an incredibly hot, dense plasma. In the first fraction of a second after the Big Bang, particle-antiparticle pairs were created and annihilated constantly. The universe was too hot for atoms to form. After about 1 second, the universe had expanded and cooled enough that neutrinos decoupled. They stopped interacting with other particles and flew freely through space. A ghostly sea of neutrinos created in the first second of the universe still fills all of space today. After about 3 minutes, the universe had cooled enough for protons and neutrons to combine into atomic nuclei. This process, nucleosynthesis, created the first nuclei of hydrogen and helium, with trace amounts of lithium and beryllium. After about 380,000 years, the universe had cooled enough for electrons to combine with nuclei, forming the first atoms. This is called recombination. Before this point, the universe was opaque. Light couldn't travel far before hitting charged particles. After recombination, the universe became transparent, and light could travel freely. This light, the cosmic microwave background radiation, is what we observe today. It's redshifted by cosmic expansion from an original temperature of about 3000 Kelvin to the current temperature of about 2.7 Kelvin. But it's still the light from the early universe, the oldest light we can observe. Analyzing this ancient light reveals what the early universe was like. We can measure tiny temperature fluctuations in the cosmic microwave background and infer the density variations that led to galaxy formation. This is how we know the age of the universe, 13.8 billion years. This is how we know the composition of the universe, about 5% ordinary matter, 27% dark matter, 68% dark energy. This is how we know the large-scale structure of the universe came from quantum fluctuations that were amplified by gravity over billions of years. All of this knowledge comes from studying light that has been traveling toward us since the universe was incredibly young. Now let me explore supernova explosions, which are among the most violent events in the universe. When a massive star reaches the end of its life, it can explode as a supernova. The explosion releases energy equivalent to the sun's entire lifetime energy output in a matter of seconds. A typical supernova explosion reaches temperatures of billions of Kelvin. It hurls material outward at velocities of tens of thousands of kilometers per second. The explosion wave propagates outward at supersonic speeds. For a few weeks or months, a supernova can outshine an entire galaxy containing billions of stars. A single exploding star can briefly be as bright as billions of normal stars. Supernova explosions are the primary mechanism by which heavy elements, iron, cobalt, nickel, and others, are distributed throughout the galaxy. Without supernovae, the universe would consist only of hydrogen and helium. There would be no heavy elements, no rocky planets, no chemistry, no life. Every iron atom in your blood was created in the core of a star and distributed by a supernova explosion. Every oxygen molecule you breathe was created in a star. Every carbon atom in your body was created in a star. You are literally made of stardust, atoms created in stellar furnaces and scattered by stellar explosions. The atoms in your body are old. They've been recycled through many stars and many explosions over billions of years. You're not just observing the universe, you're part of it. You're made of the same material that makes up galaxies and stars. Finally, let me address one more philosophical dimension of cosmic scale: the concept of meaning and purpose in a vast universe. In a universe 46 billion light years across, containing billions of galaxies, each with billions of stars and potentially trillions of planets, where is meaning? Where is purpose? This is the question that has troubled philosophers and theologians as our understanding of cosmic scale has grown. For most of human history, Earth seemed central, important, the stage on which meaningful events occurred. The vastness of cosmic space has challenged that view. But I think this challenge has been misunderstood. The vastness of the universe doesn't make individual lives meaningless. If anything, it makes them more meaningful. Consider, in a universe this large, with this many possible configurations of matter, the fact that consciousness emerged at all is extraordinary. The fact that you are conscious, capable of thought and understanding, is not inevitable. It's a product of billions of years of cosmic and biological evolution. The fact that your atoms were forged in stellar furnaces billions of years ago, that you exist in a region of the cosmos where conditions permit life, that you're capable of understanding the universe that created you. This is remarkable beyond words. Yes, you're small. Yes, you're temporary. Yes, when you die, you'll stop existing. But the atoms that make up your body will persist. They'll be recycled into new forms, new structures, new conscious beings, perhaps. You're part of a vast process, unfolding across billions of years and billions of light years. You're a manifestation of the universe's attempt to understand itself. I find meaning in that. I find purpose in being conscious, in learning, in teaching, in contributing to human understanding. I find meaning in my connections to other conscious beings, in our shared effort to understand the cosmos. The vastness of the universe is not a reason for despair. It's a reason for wonder. The universe is incomprehensibly large, and we exist within it, conscious, aware, capable of understanding. That's the ultimate answer to the question, how big is the universe? The universe is so big that we exist in it, and yet so understandable that we can comprehend its vastness. Let me discuss gravitational waves, a relatively recent discovery that's revolutionizing how we understand cosmic scale. Gravitational waves are ripples in space-time itself, created by accelerating massive objects, colliding black holes, merging, neutron stars, or the Big Bang itself. For decades, gravitational waves were predicted by Einstein's theory, but not directly observed. Then, in 2015, the LIGO experiment detected gravitational waves from two colliding black holes a billion light years away. This was extraordinary. We detected ripples in space-time from an event that happened a billion years ago, billions of light years away. The two black holes, each about 30 times the mass of the Sun, spiraled into each other and merged, releasing tremendous energy as gravitational waves. These waves propagated across space, weakening as they traveled. By the time they reached Earth, they were incredibly subtle, distorting space by less than the width of a proton over a 4-kilometer distance. Yet LIGO could detect them. Since 2015, dozens of gravitational wave events have been detected. Each one reveals information about cosmic collisions happening billions of light years away. We're using gravitational waves to study the universe in a new way, complementing observations from light. This demonstrates how cosmic scale continues to challenge us and inspire new technology. A billion light year event creates detectable ripples in space-time at Earth. The universe is connected at the deepest level. Distant events affect the fabric of space here. Now let me explore multi-wavelength astronomy, which reveals how cosmic scale is illuminated in different ways. The universe emits light in many forms: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. Each wavelength reveals different phenomena. Radio waves from distant galaxies tell us about their composition and dynamics. Infrared observations reveal newly forming stars hidden in dust. Visible light is what our eyes see. Ultraviolet reveals hot, energetic processes. X-rays from black holes and neutron stars show the universe's most extreme environments. Gamma rays reveal the highest energy events. A complete understanding of cosmic scale requires observing across all these wavelengths. A galaxy might look one way in visible light, but completely different in radio or X-rays. Different wavelengths reveal different layers of cosmic structure. Modern astronomy requires satellites and instruments across the entire electromagnetic spectrum. The James Webb Space Telescope observes in infrared. X-ray telescopes like Chandra reveal X-ray sources. Radio telescopes like ALMA observe molecular clouds. Together, they create a comprehensive picture of the universe. This diversity of observation methods reflects the complexity of the universe. No single type of observation can reveal everything. We must study the cosmos from multiple angles, using multiple techniques across the entire spectrum. The universe is not just large, it's complex. It's filled with structure at every scale, processes occurring across all wavelengths, phenomena we're still discovering and learning to interpret. Let me also address how our understanding of cosmic scale has evolved and continues to evolve. 500 years ago, we thought the universe was immutable and unchanging, with Earth at the center. 200 years ago, we realized the universe was much larger and that Earth orbits the Sun. 100 years ago, Hubble discovered that galaxies exist beyond the Milky Way, and the universe was expanding. 50 years ago, we discovered the cosmic microwave background radiation, evidence of the Big Bang. Today, we know the universe is 13.8 billion years old, 46 billion light years across, containing billions of galaxies. Tomorrow, future telescopes and technologies will reveal even more. We might discover signs of extraterrestrial life. We might find gravitational waves from the Big Bang. We might map the large-scale structure of the universe more completely. Each generation's understanding of cosmic scale has been upended by new discoveries. There's every reason to expect future discoveries will continue surprising us. The universe is not just large in space and time, it's also large in its capacity to surprise us, to challenge our understanding, to inspire wonder. For most of human history, we've been stuck on one planet, orbiting one star, in one galaxy. We couldn't see far. We couldn't understand much. We were trapped by our own limitations. But through the power of science and observation, we've transcended those limitations. We've built telescopes that show us billions of galaxies. We've calculated the age and size of the universe. We've inferred what happened near the Big Bang. We've discovered that the universe is expanding and accelerating. This achievement This ability to understand our cosmic context is remarkable. It's a testament to human curiosity, ingenuity, and the power of systematic observation and reasoning. As I contemplate all this, the size of the universe, our place within it, the knowledge we've acquired, I return to that 8-year-old child in the field, struck by cosmic vertigo. That child felt something true. The vertigo was justified. The universe really is that large. The implications really are that staggering. But now, as an adult, I understand that this vastness is not a source of despair. It's a source of inspiration. We live in an era where we can understand our cosmic context. We live at a time when stars are still shining, when life is still possible, when consciousness is still emerging and evolving. We exist in a golden age of the universe early in its history when complexity is still being created, and we have the ability to understand what we observe. That's extraordinary. That's remarkable. That's something to appreciate and build upon. The universe is 13.8 billion years old. It's 46 billion light years across. It contains hundreds of billions of galaxies, each with hundreds of billions of stars. Most of it is empty space. Most of its energy is in forms we don't understand. And yet, in this vast cosmos, consciousness has emerged. The universe has become aware of itself. Through us, through any other conscious beings that might exist, the universe contemplates its own nature. We are part of something larger than ourselves. We're part of a cosmic story that began 13.8 billion years ago and will continue for trillions of years into the future. We're made of star stuff. We're conscious beings in an unconscious universe. We're observers of vast cosmic scales. And that's beautiful. Let me revisit the specific techniques we use to measure cosmic distances and give concrete examples of how accurate they are. The parallax method works for nearby stars. We measure the position of a star at one point in Earth's orbit, then measure again 6 months later when Earth is on the opposite side of its orbit. The star's position shifts slightly. Using trigonometry and knowing Earth's orbital radius, we calculate the star's distance. Proxima Centauri shows a parallax angle of about 0.768 arcseconds. An arcsecond is 1/3600th of a degree. This tiny angle, measured with high precision, tells us Proxima Centauri is 4.24 light years away. For farther stars, parallax becomes too small to measure accurately. This is where Cepheid variables come in. These are stars that pulse in brightness with a regular period. The period correlates with the star's actual brightness. We observe the period and measure how bright the star appears. From this, we calculate its distance. When Edwin Hubble discovered Cepheids in Andromeda in 1924, he measured their periods, compared them to similar Cepheids in the Milky Way, whose distances were known from parallax, and calculated Andromeda's distance. He found it was 2 million light years away, far beyond the Milky Way. This single discovery expanded our cosmic perspective enormously. For even more distant galaxies, we use Type 1a supernovae. These explosions have consistent peak brightness. When we detect one in a distant galaxy, we measure how bright it appears to us and calculate its distance. These methods form a cosmic distance ladder. Each rung extends our reach farther into space. Each measurement depends on the previous rung being accurate. The precision of these measurements has improved dramatically. The Hubble Space Telescope's famous Hubble Deep Field image showed about 3,000 galaxies in a tiny patch of sky the size of a grain of sand. By using these distance measurement techniques on galaxies in that field, astronomers determined their distances, some as far as 13 billion light years away. This demonstrates how measurement techniques stack on top of each other, building a comprehensive model of cosmic distances and structure. Now, let me reflect on the role of curiosity in driving our cosmic understanding. Humans are curious creatures. We want to know, we want to understand, we want to explore. This basic drive, curiosity, has been fundamental to all scientific progress, from ancient astronomers tracking the planets to modern cosmologists mapping the universe. The desire to understand has motivated human inquiry. The question, how big is the universe, represents this fundamental human curiosity. We look up at the night sky and wonder. We're not content with the sky just existing as a backdrop to our lives. We want to know what's there, how far it is, how it all works. This curiosity has driven us to build increasingly sophisticated tools. From the naked eye to telescopes to modern space telescopes and arrays of instruments, we've extended our ability to observe the cosmos. And each new observation raises new questions. We learn the universe is larger than we thought, so we wonder how much larger. We discover it's expanding, so we wonder why. We find most of it is made of dark matter and dark energy, so we wonder what those are. Science is a journey of discovery, where each answer raises new questions. The story of cosmic scale is a story of increasing revelation, each generation discovering that the universe is larger, more complex, more wonderful than previously imagined. Now let me compare different time scales to illustrate how vastly different cosmic time is from human time. A human lifetime is about 80 years. This is the span of one human's experience. A recorded history is about 5,000 years. This is the span of civilizations and documented events. Human civilization is about 10,000 years old. This is how long humans have lived in organized societies. Modern humans, humans with our current biology, have existed for about 300,000 years. All life on Earth has existed for about 3.5 billion years. This is the entire span from the earliest single-celled organisms to humans. The solar system has existed for about 4.5 billion years. This is how long the sun and its planets have existed. The universe has existed for about 13.8 billion years. This is the age of all time and space and matter and energy. Let me put these on a scale. If the universe's age since the Big Bang is represented by a line 1 meter long, then the age of Earth is represented by about 0.32 meters. The age of life on Earth is represented by about 0.25 meters. Human civilization is represented by a line just 0.0007 meters long, less than a millimeter. A human lifetime is represented by a line 0.0000058 meters long, a few micrometers. On the scale of cosmic time, human lives are invisible. We are briefer than the blink of an eye. We exist for an immeasurably small fraction of cosmic history. And yet, in that immeasurably brief time, consciousness emerged. The universe became aware of itself. This perspective is both humbling and uplifting. We're temporary, yes. Our individual lives are brief, but we're conscious during that brief time. We can think, understand, marvel at the universe. That's extraordinary. Let me conclude by returning to the fundamental question one more time. How big is the universe? The observable universe has a radius of about 46 billion light years. It contains about 100 billion galaxies, each containing about 100 billion to 1 trillion stars. It's roughly 13.8 billion years old. It's expanding, and the expansion is accelerating. But size can be measured in many dimensions. The universe is vast in spatial extent. It's deep in time. It's complex in structure. It's mysterious in composition. Most of it is made of things we don't understand. The universe is large in potential. Given billions of years, complexity can emerge. Given trillions of planets, life might emerge on many of them. But perhaps most importantly, the universe is large in comprehensibility. Despite its vastness, despite the limitations of our evolved perception, we can understand it. We can measure it, model it, build theories that explain it. The ability to contemplate the cosmos, to understand its vastness, to place ourselves within it, this is the defining achievement of human consciousness. That's what how big is the universe really means. It's not just a question about numbers and distances. It's a question about our place in the cosmos, about what it means to be conscious observers of vast scales, about the remarkable fact that the universe has become aware of itself through us. The answer is the universe is incomprehensibly large, and we are part of it, and that's beautiful. Let me explore the discovery of cosmic expansion in more detail, as this is one of the most revolutionary observations in the history of science. In the 1920s, astronomers were puzzled by observations of distant galaxies. They noticed that the light from these galaxies was redshifted. The wavelengths of light were stretched, shifted toward the red end of the spectrum. This suggested the galaxies were moving away from us. But why would galaxies be moving away? The prevailing assumption was that the universe was static and unchanging. Edwin Hubble, observing with the Mount Wilson telescope in California, systematically measured the distances and velocities of nearby galaxies. He found a pattern. The farther away a galaxy was, the faster it was receding. This relationship, now called Hubble's law, implied the universe itself was expanding. This was revolutionary. It meant the universe wasn't static. It was dynamic, changing, evolving. It also meant that if we ran the clock backward, all galaxies would have been closer together in the past. Run it all the way back, and they would have all been at the same point, the Big Bang. Hubble's discovery transformed our understanding of the universe. Suddenly, the universe had a history. It had an origin. It was evolving according to physical laws that we could study. This discovery was so profound that it took decades for its implications to be fully appreciated. The universe had an origin. It had an age. It was expanding. These weren't features we'd suspected. They were forced upon us by observations. Later, observations revealed that the expansion wasn't slowing down due to gravity. It was accelerating. This led to the discovery of dark energy, one of the greatest mysteries in physics. What is dark energy? We don't know. Possibilities include the cosmological constant, a property of empty space itself, a kind of energy density that's intrinsic to space. As space expands, more space is created, and if space has energy density, the total dark energy increases. Quintessence, a dynamic field that varies in space and time, producing an effect similar to a cosmological constant, but with more flexibility. Modified gravity, perhaps general relativity, doesn't work correctly at cosmic scales, and what we interpret as dark energy is actually a failure of our theory of gravity. Unknown physics. There might be phenomena we haven't discovered yet that explain cosmic acceleration. The fact that the universe is mostly made of something we don't understand is both humbling and exciting. It means there's more to discover. Our current understanding, despite being sophisticated, is incomplete. Now let me reflect on what cosmic scale means for the future of human understanding. We live at a special moment in cosmic history, a moment when consciousness has emerged and is beginning to understand the universe. Future generations, thousands or millions of years hence, might develop technology we can't imagine. They might be able to directly observe the regions beyond the cosmic horizon, extending our knowledge of the universe, detect signals from alien civilizations, answering one of our deepest questions: are we alone? Develop methods of faster than light travel or communication, transcending the cosmic distance limitations we currently face. Understand the nature of dark matter and dark energy, solving current mysteries. Create artificial intelligences that can think about cosmic scale in ways our current brains cannot. What we learn in the next 100 years will lay the foundation for all future discoveries. The questions we ask now, the observations we make, the theories we develop, these will guide research for millennia. We're living in a pivotal era. We've just begun to understand our cosmic context. The journey is far from over. Finally, let me reflect on what contemplating cosmic scale means for me personally. When I think about how big the universe is, when I really let the scale sink in, I experience a mixture of emotions. Awe, certainly, humility, wonder, a sense of connection to something vast and beautiful. But I also experience something else, a sense of responsibility. If consciousness is rare, if observers are uncommon, then those of us who are conscious have a responsibility to understand, to preserve knowledge, to pass it on. We're the universe's way of knowing itself. We're temporary manifestations of cosmic matter and energy that have organized themselves in ways complex enough to generate consciousness. We're here for a brief moment and then we'll cease to be. But while we're here, we can understand, we can think, we can marvel. I think that's enough. That's more than enough. That's extraordinary. When I look at the night sky now, I see not just distant lights, but vast structures, incredible distances, events happening billions of years in the past and billions of light years away. I see the universe in all its complexity and beauty. And I see myself as part of that. Small, yes, temporary, yes, but part of it nonetheless. I'm made of the same matter that makes up stars and galaxies. I'm conscious at a moment when consciousness is rare. I have the privilege of understanding my cosmic context. That's what it means to contemplate cosmic scale. It's not depressing. It's inspiring. It's beautiful. It's meaningful. The universe is incomprehensibly large. I am incomprehensibly small, and yet I exist, conscious, aware, capable of understanding both. That's the answer to how big is the universe? It's big enough to contain billions of galaxies, billions of stars per galaxy, billions of planets per star. It's big enough that distances are measured in light years and ages in billions of years. It's big enough that most of it remains mysterious. And it's big enough to contain you, conscious, aware, capable of understanding it. That's remarkable. That's beautiful. That's enough. Let me explore one more aspect of cosmic scale that deserves deeper attention: the concept of cosmic neighbors and what makes something nearby at cosmic scales. When we talk about galaxies being near or far, we're using terms that are meaningful only at cosmic scale. Andromeda is our nearest galactic neighbor at 2.5 million light years away. At this distance, light takes 2.5 million years to travel from Andromeda to us. If Andromeda is near, what does that tell us about cosmic distances? It tells us that galaxies are vastly separated. Even our nearest large galactic neighbor is so far that its light takes longer to reach us than modern humans have existed. But within our own galaxy, there's a local neighborhood of smaller galaxies. The Large Magellanic Cloud is about 160,000 light years away. The Small Magellanic Cloud is about 200,000 light years away. These are smaller galaxies orbiting the Milky Way. From the perspective of the Milky Way, these galaxies are close companions. From our human perspective, they're millions of times farther than Pluto. The scale changes depending on what you're measuring against. Measure against human dimensions, and even the moon is incomprehensibly far. Measure against galactic dimensions, and Andromeda is practically a neighbor. This scaling of perspective is important for understanding cosmic scale. There's no absolute near or far. Everything is relative. In our local region of the galaxy, there are about 46 nearby stars within 12 light years of Earth. These are our stellar neighbors. At the galactic scale, they're clustered together. At the interstellar scale, they're widely separated. The Orion Nebula is about 1,300 light years away. Not close by galactic standards, but visible to the naked eye as a fuzzy patch in the constellation Orion. Stars are being born in that nebula right now, billions of light years into the cosmic past as we observe it. The Andromeda Galaxy is visible to the naked eye as well, appearing as a fuzzy patch in the night sky. It's the most distant object we can see with our unaided eyes. A collection of 1,000,000,000,000 stars, 2.5 million light years away, made out faintly in our vision. These observations, seeing vast structures billions of light years away, just by opening our eyes and letting them adapt to darkness, remind us of how vast the universe is and how much of it we can perceive, even with basic human senses. Let me also explore the concept of looking back in time more deeply, as this is one of the most profound implications of cosmic scale. When we observe distant galaxies, we're not seeing them as they are now. We're seeing them as they were billions of years ago, because that's how long their light took to reach us. A galaxy 10 billion light years away appears to us as it was 10 billion years ago. If the universe is 13.8 billion years old, then we're seeing that galaxy as it was when the universe was only 3.8 billion years old. This means astronomy is a form of time travel. We can see the distant past by looking at distant parts of the universe. The cosmic microwave background radiation is the most extreme example of this. It's light that was emitted 380,000 years after the Big Bang. We're seeing light that's been traveling toward us for 13.8 billion years. We're observing the universe when it was 380,000 years old. Observing the cosmic microwave background is like looking at a snapshot from the early universe. The tiny temperature fluctuations in that radiation represent the seeds of galaxies, regions slightly denser than average that would eventually collapse into galaxies under gravity. We're looking at the baby picture of the universe. We're seeing what it looked like when it was incredibly young. This is how we know the universe's history. We don't need time machines. We just need to look far away. Now let me address one final crucial aspect of cosmic scale: the recognition that our current knowledge, despite being sophisticated, is incomplete. For centuries, we've been steadily discovering that the universe is larger and more complex than we previously thought. Each generation makes observations that overturn the previous generation's understanding. We thought stars were at fixed distances on a celestial sphere. We discovered some were closer and some farther. We thought the Milky Way was the entire universe. We discovered billions of other galaxies. We thought the universe was static and unchanging. We discovered it was expanding. We thought the expansion would slow due to gravity. We discovered it was accelerating. We thought we understood the universe's composition. We discovered 95% of it is made of things we don't understand: dark matter and dark energy. If history is any guide, future discoveries will surprise us. We're not at the end of our cosmic understanding. We're still at the beginning. The universe is larger than we think, more complex than we understand, more mysterious than we realize. And that's exciting. That's wonderful. That means there's more to discover. That means the frontier of human knowledge extends far into the future. We live at a moment when cosmic mysteries are solvable. Technology is advancing rapidly. New telescopes and instruments are coming online. We're on the verge of potential breakthroughs in our understanding. What might we discover in the next 50 years? 100 years? 1,000 years? We don't know. But the fact that we can contemplate these possibilities, that we can design experiments to test them, that we can build instruments to observe them, that's a testament to human ingenuity and our drive to understand. The universe is incomprehensibly large. Our understanding is still in its infancy, but we're learning, we're discovering, we're slowly, very slowly, beginning to grasp our cosmic context. That's the real answer to how big is the universe. It's bigger than we can imagine, and we're just beginning to understand it. And so we arrive at the answer finally after all this exploration. How big is the universe? The universe is 46 billion light years across in the observable direction. It contains billions of galaxies, each containing billions of stars. It's 13.8 billion years old, and it's still expanding, still evolving, still creating new structures. But numbers alone don't capture the true meaning of cosmic scale. The universe is big enough to be mostly empty, yet complex enough to support galaxies and stars and planets and life. It's old enough that light from the most distant galaxies shows us the universe when it was young, yet young enough that stars are still being born. It's vast enough that we're utterly insignificant, yet ordered enough that we can understand it through science and observation. The universe is all of this and more. It's simultaneously incomprehensibly vast and somehow knowable to minds like ours. And we exist within it. We are part of it. We are, quite literally, the universe contemplating itself. That's how big the universe is. When you lie in a field at night and look up at the stars, as that 8-year-old did all those years ago, you're seeing something remarkable. You're seeing light that has traveled for years or decades or centuries or millions of years to reach your eye. You're seeing structures, stars, galaxies, cosmic phenomena, separated by distances that dwarf anything in human experience. And yet you can understand it. You can learn the physics, grasp the scales, build models of how it all works. You can contemplate your place in this vast cosmos. That's the miracle of consciousness. That's the achievement of human understanding. The universe is incomprehensibly large, but it's also comprehensible to minds like ours. And that's the most extraordinary thing of all. So here we are at the end of this exploration. We've journeyed from the moon at 384,000 kilometers to the edge of the observable universe at 46 billion light years. We've explored cosmic scale through numbers, analogies, physics, and philosophy. We've learned that the universe is vast beyond human intuition. We've learned that it's mostly empty space. We've learned that it's mostly made of things we don't understand. We've learned that consciousness, as far as we know, is rare. But we've also learned that this vastness is knowable. Through science, observation, and reason, we can understand our cosmic context. We can measure distances to galaxies billions of light years away. We can infer the age of the universe to within 100 million years. We can model how it all works. That's the remarkable achievement of human consciousness in this vast cosmos. We can understand, we can know, we can comprehend what we observe. That's worth contemplating. That's worth celebrating. That's remarkable. The universe is incomprehensibly large, and we are incomprehensibly small. And yet, here we are thinking about it all. That's beautiful. That's meaningful. That's enough. I think that's the message I'd want to leave you with. After all this discussion of cosmic scale, the universe is vast, incomprehensibly, immensely vast. But we're not lost in it. We're not meaningless because of it. We're remarkable because of it, because we can know it, understand it, appreciate it. That's what I think about when I look at the night sky now. Not insignificance, but wonder. Not emptiness, but connection. Not meaninglessness, but meaning found in understanding, in consciousness, in the remarkable fact that we exist at all. The universe is 46 billion light years across, and we are here, able to comprehend it. That's extraordinary. Thanks for watching.